Hello and welcome to CoreTalks, CoreAVI's technical podcast series. Today we're going to talk about component screening, which is a core part of CoreAVI's business model. We have with us today Mike Pine, Senior Director of Strategic Accounts, and Neil Stroud, the General Manager of Automotive and Embedded here at CoreAVI. Welcome both.
Hey, Marybeth.
Thank
Hi,
you.
Mike.
Let's start with the basics. Why is temperature screening so important, and why does CoreAVI do it instead of customers doing it for themselves?
I'll take that one. So the history in aerospace is kind of fascinating, at least to me, because in the early days of electronics for aerospace, there was a whole family of electronic circuits and chips geared for that environment, which had real extreme temperatures and a few other things. As the electronics industry grew, the vast majority of how integrated circuits and chips were used in commercial devices. And so eventually the aerospace community lost an entire source of supply of chips that would meet their needs. So facing that dilemma, these aerospace companies, they still wanted the latest and greatest functions, the latest and greatest processors, fastest memories, and so forth. But they couldn't necessarily find chips that would meet their environmental needs, specifically temperature. So that created this gap where companies like CoreAVI said, well, these chips can oftentimes still work. It's just a question of screening. And so you find in a given production lot those chips that can work over an extended temperature range. You test those, you screen those, you bin those accordingly, and then you make those available for customers, aerospace customers in particular, to use. Now, some aerospace customers will do that screening on their own, but there's a severe economic penalty. If you put, say, a commercial chip onto an aerospace circuit board or component assembly, and it fails sometime in testing due to a temperature sensitivity, aerospace customers know that the cost of repairing and troubleshooting and replacing a part like that easily gets into the thousands of dollars, even a small thing. So having those parts pre-screened to meet the temperature range that you know it's going to have to work in and that you know you're going to test to actually saves them a significant amount of money.
I think that was very well articulated, Mike. Thanks for explaining that. And I mean, you focused a lot on the avionics industry as requiring this. Of course, there are other embedded applications out there that require wider temperature ranges than traditional commercial, which I think of as kind of 0 to 70 degrees C. If I think about the automotive industry, for example, we all drive cars, and typically they can be in extreme temperature conditions, whether that's hot or cold. So again, those devices, those SoCs, need to function at wider temperature ranges. But I think one of the key differences I see with automotive is typically the suppliers of those SoCs do seem to be qualifying their parts to, minus 40C to, plus 85, which in a lot of cases is okay, but I still see avionics as requiring, an even wider temperature range, which is, I guess, why we've invested the time and effort to put CoreAVI in this process and provide this additional service. So, how did we get into this in the first place? What's the history of CoreAVI getting into screening?
Well, that's a great question, Neil. I think CoreAVI's history of developing drivers and libraries for graphics chips and our relationship with customers demanding high levels of security and safety determinism. The partnerships we developed early on with GPU manufacturers was key to being able to do effective screening. Anybody could screen a GPU, but you're going to probably create test software that's more a system level or high level function. What you really want to be able to do if you intend on screening parts effectively and with great integrity is use a component level software test. And that's usually only available from the manufacturer of the part itself. And so because CoreAVI had an intimate partnership with some of these GPU manufacturers, that relationship allowed us access to those software test routines that could do extensive component level test screening. So yeah, anybody could put a part through temperature, but what's key is being able to run test routines that reflect what the manufacturer intended to exercise full functionality. So that pairing of our relationship with these GPU manufacturers with our customer base that wanted these screen parts, because for the most part, the volumes required were so low that, a big company, an AMD or an Intel, they're probably not going to want to do extended temperature testing for a lot of their product lines just because the volumes didn't justify it. So we provided a service that our partners, the manufacturers of components, appreciated, so they get to sell more chips, and we were able to tailor tests to our aerospace and other customer and marketplace needs that reflected that.
Yeah, and I think you started to touch on the process a little bit. Of course, as you kind of alluded to, it's not a case of just getting these chips and then throwing them in a freezer and throwing them in an oven and seeing if they work when you get them out. It's a little bit more involved in that. You've got to stress the device, run a representative workload on it of some description, and screen at the same time. So can you kind of elaborate a little bit more on the process? Obviously, without there's some crown jewel stuff here as well, but to
Sure.
just touch on the process of what's involved in the screening.
Well, CoreAVI is in a somewhat unique position as perhaps a bridge between an end user, a customer with very specific application in mind. CoreAVI has great visibility into that because of our primary product line, libraries and drivers, and working with the system and software components. And so we can see end use applications. And so when we craft, say, a temperature profile, we pretty much know how our end customers are going to use that. We know that they're going to start up after, I'll say, a cold soak at -40 because they could be on a tarmac for hours and hours at -40. And so we craft our temperature profile to reflect what we think is our customer's use case. We know a lot about how our manufacturer partners use and do their screening. So we can bridge that gap in ensuring that our screening matches the end use profile pretty closely. And so it's a mixture of not just the temperature settings and power settings, but you're carefully analyzing which parts of the device are being exercised and when, and how many times as you ramp up are you exercising certain components. And admittedly, there's a lesson learned process that we go through as we screen parts and we see yields and we get feedback from customers. We oftentimes modify those test profiles to produce the best integrity we can for these devices. So our customers can, with confidence, put these parts on a circuit board and put them through their burn-in or environmental stress screening and know that those parts are going to work because they've been properly screened.
Yeah, I guess that's a key point, isn't it? Because we don't really have visibility of the end application. So any testing and screening we do is kind of out of context. It's somewhat generic, and then it gives the end customer the confidence that when they do go through their environmental testing, that we've done the homework for them, and at least our parts and our homework should pass the
Yeah.
tests.
And Neil, just to add one part to that, for our more sophisticated customers, they'll ask, so how do you maintain, the die temperature, which is obviously the manufacturer's data sheet is really what rules all things. And our process mimics what the manufacturers themselves do. So we control in a very intimate way the actual die temperature itself with a very specific thermal management unit sits right on top of the device. And so we get this question a lot. Well, you're just ensuring the package is at this temperature, right? No, we ensure the die is at those data sheet temperatures and the specifications of extended temperature range. So we're real proud of that because it's a kind of an expensive process to go through and an extensive one, but it ensures that real close and tight control of the die temperature.
Right. Yeah, and I guess that kind of plays into the economics of the screening. If we've done that homework on behalf of the customer, they've got that level of risk reduction when they do that system level verification, I guess, and that can save them a lot of time and money and effort on rework as well, right?
Absolutely. Yeah.
Okay, good. So we've talked about temperature screening. Are there other types of screening out there?
Yeah, as we are learning the latest and greatest electronic devices, as geometries shrink, we're seeing new parameters. They may still be temperature related, but they don't fall in the rather simplified, extremes of, just -40 to +85 or whatever. Several manufacturers doing these very aggressive geometry shrinks are seeing a new phenomena, I'll call it, where components within these massively dense devices are showing a sensitivity to temperature range. And it's the nature of components like a phase lock loop. So these particular functions on almost every microcircuit, certainly every processor, these functions are showing a sensitivity to temperature in that they initialize with certain conditions, and those are temperature dependent. So if you start up at, let's say, 0 degrees C, that phase lock loop and appropriate clock circuits are going to initialize all their parameters based on that temperature. And then as the device heats up, those parameters tend to change. And so with these fine geometry devices, they're seeing limits to where if you start at 0, but as you approach, let's say 90 degrees C from that original point, those operating parameters, those functions now are pushed to their limits. And many manufacturers are saying, okay, after you extend through a certain range, regardless of where you started, those sensitive components like phase lock loops need to be reset or reinitialized for the new range or the new temperature that you're at. And so this is oftentimes called dynamic temperature range, or DTR. And so as you can see, a device rated for minus 40 to plus 85, that range is 125 C, the range. And so the manufacturers are more or less telling users, especially in the aerospace community, if you go past that range of, let's say, published in the data sheet of 90 degrees C, you need to restart the device so that PLL and other components like it can reinitialize and adapt to the new temperature. Well, as you might imagine, some of our aerospace customers are not keen on restarting something like, a computer that's generating flight information on a cockpit display. They don't want the cockpit, the display can't just go away for a few seconds. You tell the pilot, hey, stand by. We're resetting everything because of a new temperature that we've achieved. So our efforts are to address something like this. So it's a new phenomena. We want to be able to screen for this thing called DTR as it becomes I'm not going to say a problem, but it's certainly an issue in that as manufacturers create these parts with these wide temperature ranges, which is a good thing, but then there's a caveat like, oh, by the way, when you pass a certain temperature range or extent, you're going to need to reset the device. So CoreAVI is addressing this by screening a system-on-chip device with a known and published DTR, or dynamic temperature range limit, by screening those parts. And so we're exercising the part with full functionality. We're starting at a real cold temperature, obviously the lowest it's published, so minus 40 in most cases. And then we're testing it as we increase the temperature, going well beyond the published dynamic temperature range limit in the data sheet. And then for those parts that pass, we can sell them as DTR screened. And so that's a new kind of market space that our customers are having to face and deal with that we're trying to address.
Yeah, it's interesting, isn't it? Because it's kind of a physics limitation, right? We all, those of us who went through electronics at college and university, understand how PLLs function, and of course, it's a physics thing that they start to go out of phase or have the potential to go out of phase as the temperature changes. So, for the most part, this wouldn't impact everyday systems that these components go into, but as soon as you start talking about mission critical, then there's a risk there for sure. And the example, I think perhaps told me, the example is on a primary flight display in an aircraft. If you're on final approach and all of a sudden your system decides to reboot because of a DTR function happening, that's generally not a favorable thing. So if we can manage around that, it obviously reduces that risk significantly. And the CoreAVI screening capabilities to screen out this feature, this capability is seen as a good thing. So is it gaining traction with our customers out there? Is this something that they see as a positive thing?
Yes, we have several orders, fairly large volume orders. And maybe just a note here, Neil, there's a different economic force in play. So when you screen, say, traditionally GPUs for extended temperature, you're more or less addressing a reliability issue. You want to save them from parts failing in a burn-in or environmental stress screen. The DTR screening is a different economic driver in that you probably, if you couldn't accept the DTR limit without our screening, you'd have to choose a different part. And so you might be unable to get access to the best technology, the fastest, lowest power technology because of this DTR limit. So now your economic equation is like, I just can't get this technology. It can't go into my system. I'll have to compromise on a very fundamental level which parts I can choose. So yeah, I think that's what's going on with our customers' view of this. Is they're allowed access to this solid state-of-the-art technology, DTR issue aside, because of what CoreAVI offers in terms of screening.
Right. And I guess it's important to note as well that once we've screened for DTR on a given component, that component will never manifest a DTR event, right? We can make that statement categorically once it's been through that screening that it's good forever, right?
Oh, yeah. We started this with fairly detailed and intimate conversations with the semiconductor experts at some of these manufacturers.
Mm-hmm.
And as we proposed this screening process for something like DTR and said, hey, once it works and we prove it works in these conditions and doesn't need to reset, are we good to go? And they said, yes, it's a forever kind of parameter. And those functions or features that you might say are DTR sensitive, they don't change with time. They're clearly a manufacturing kind of sensitive thing. And once you've manufactured the part and you do test it, it doesn't change or degrade with time.
Yeah, that's a really important point because we think about from a reliability perspective, silicon wear out over time, and obviously the number of service hours that these kind of components go into in the aviation market segment. These things can be flying for years and years and years. So that's an important point that once it's screened for good. Okay. What about troubleshooting? I know this is something we've touched on a little bit within our business. Troubleshooting for screened parts, so around rescreening or failure analysis. Do we have a role to play in that as well?
Well, I think so. As a fairly small company and fairly nimble, we can offer services in that area because we're already set up to do functional test over temperature. So for a customer that says, hey, this part, it misbehaves at a certain temperature range, or when it passes through a temperature threshold, we can't explain it. We'd like to do some further investigation. Yeah, CoreAVI can offer some experience there. Not only do we have the test environment, because of our software expertise, especially at the lower levels of drivers and libraries, we can exercise the part in a custom fashion as our customers might dictate. So yeah, that's been asked of us on a couple of occasions with some of our older GPUs where customers have found a problem, and I'm not going to say necessarily with temperature per se, but they found a system fault and said, hey, we can't explain this, and all of our efforts to exercise the part in a certain way or ring out a given fault have failed. So they'll come to us and say, can you reproduce this? And if you do, can you create some diagnostics that might tell us more about the part anomaly? And generally, we're not detecting part failures in the traditional sense. We're looking at maybe the system usage of features and functions within a part and exposing, and I don't mean to be critical of a customer's application, but sometimes we're finding applications that are misbehaving in a way that we can detect and maybe they weren't able to.
So I think, as you said right at the beginning of the conversation, I think all the work we've done on screening to date has been based around discrete GPUs, which we know are used, predominantly in the avionics space, and a good reason for doing that. Of course, we live in a world that's migrating more towards SoC, system on chip, where there's integration of CPU, GPU, NPU, memory, peripherals, all on one device. So I guess at some point, discrete GPUs, at least in the embedded space, go away. So, what does the future hold for Core AVI from a screening perspective? Do you see a need to be screening those SoCs in future, or what's our role in the future?
A great question. It's going to be an interesting pivot for us as we're a known quantity for GPU screening. SoC screening is also in our wheelhouse. Clearly, the migration to SoCs, which address the power issues more than a discrete CPU talking to a discrete GPU, the capabilities of these SoCs where they're combined is really impressive. So that's a focus of CoreAVI's clearly for software. A lot of initiatives going on to address the SoC as the primary engine for both processing and graphics. The SoC is the fundamental element for neural networks and machine learning and all of that. So yeah, we're watching that migration real closely and have launched for at least one SoC a really intensive screening process. Now, there'll always be those environmental requirements that may go beyond the data sheet. And for many SOCs, that's not going to be a problem. I think, say, for the automotive industry, you're going to see those extended temperature ranges addressed. Now, the specific performance of functions like the PLLs and this DTR thing are going to continue to be something we'll watch closely for and be prepared to address. And so that's the great thing, that we've already started with this non-extended temperature screening, and now it's a DTR screening of an SOC. And as we gain experience there and work closely with our manufacturing partners and learning more about some of the physics involved here, I think we're going to be well positioned to just, again, bring all of that legacy knowledge forward to address whatever horizons we don't really understand yet, or we haven't really come across with yet. But I know they're coming, and so I think CoreAVI would like to believe we're well positioned to address whatever pops up in our future.
Yeah, no, I think you're right. I think this need isn't going to go away. I think we have an ongoing service to provide here. It's just going to change as the requirements change over time, and we adapt to what's available in the market as far as supply, but also the needs of our customers as well. So I agree, this is an ongoing role that we have to play. Okay, thank you, Mike. I'm going to hand back to Mary Beth to wrap us up.
So, a special thanks to our guests today, Mike and Neil, for this session on component screening, and we hope our listeners have a better understanding of what screening is and why it's important. Stay tuned for more technical insights in the next CoreTalks podcast episode in our series. Thanks for listening.